Okay, so picture this. You're making your grandma's famous casserole, right? The one with all the cheese on top.
Yeah.
You pop it in the oven expecting, golden brown perfection, but instead,
Oh, disaster.
total disaster. It's a charred mess. Turns out there's a whole science behind avoiding culinary disasters like that, and it's all about heat transfer.
And it's not just for aspiring chefs. Understanding how heat moves and behaves is crucial in tons of fields.
Especially in pharmaceuticals, which is what today's deep dive is all about.
Exactly. We're going to be taking a look at, well, actually, a deep dive into a real university-level course document on industrial pharmacy.
Like getting a backstage pass to a real university course.
Exactly.
We're going to break down complex concepts from this course in a way that hopefully you find interesting.
And practical, even if you're, not planning on becoming a pharmacist anytime soon.
Okay, so let's unpack this. What is heat? I mean, besides the reason we avoid wearing black on a scorching summer day.
Right. So at its core, heat is energy. It's the kinetic energy of molecules in motion.
Kinetic energy meaning?
Meaning movement. The more those molecules are jiggling and bouncing around, the more heat they generate. And, of course, the higher the temperature.
So it's like a microscopic dance party happening in, like, my coffee cup.
Yeah.
The hotter the music, the wilder those molecules are moving.
Exactly. And we can actually measure that heat energy.
Yeah.
Just like we measure the energy in our food in calories, we measure heat energy using a unit called joules. Joules. Now, joules are actually pretty small units. It's like trying to measure the distance between, say, New York and Los Angeles in millimeters.
Yeah.
You end up with a ridiculously long number. That's where kilojoules and megajoules come in that give us more practical scale, especially when we're talking about like large-scale industrial processes.
Makes sense. Now, the source material we're looking at today, it mentions this thing called absolute zero, which sounds kind of intense.
It's a fascinating concept.
It's basically the ultimate chill zone, right? Where a substance theoretically has zero heat, no molecular motion whatsoever. Kind of makes me think of cryogenics, like freezing things to super low temperatures.
It's an interesting comparison. Absolute zero is more of a theoretical limit. We can't quite reach it in reality.
Yeah.
But cryogenics does get us incredibly close, which is pretty amazing. It opens up all sorts of cool possibilities in science and medicine.
Definitely cool. So speaking of extremes, let's talk about how heat naturally seeks balance. Our source puts it like this. Nature hates a temperature difference.
It's true.
What does that mean exactly?
It's all about achieving equilibrium. Heat naturally flows from hotter objects to colder ones, and it keeps flowing until they've evened out.
It's like nature's way of playing kissmaker, always trying to smooth things over.
Exactly.
So, like, my hot cup of coffee will eventually cool down to room temperature because the heat is transferring from the coffee to the surrounding air until they're, like, in harmony.
Precisely. That's heat transfer in action. It's this constant striving for balance that influences so much of the world around us.
And speaking of heat transfer, our source dives into the nitty-gritty of how heat actually gets around.
And there's more than one way, right? It's not just like one size fits all.
Right. There are three main ways heat gets transferred: conduction, convection, and radiation.
Okay, so 3 different ways heat can travel.
And here's the thing, they don't always operate solo. Often, it's a tag team effort.
Like a heat transfer party.
Exactly.
Everyone's invited. So let's break these down one by one. First up, conduction. What's the deal with conduction?
Okay, so imagine a bunch of molecules just vibing, just kind of shaking back and forth. Conduction is basically those molecules bumping into their neighbors and passing that energy along.
So it's like a chain reaction.
Yeah.
And it's the primary way heat travels through solids.
Okay, so like if I touch a hot stove, don't do that, by the way.
Please don't.
The heat from the stove is being conducted to my hand through what, direct contact?
Direct contact, exactly. Now, here's where things get interesting. Different materials conduct heat at different rates, and that's where the concept of thermal conductivity comes in.
Thermal conductivity.
Thermal conductivity. It's basically a measure of how easily heat can flow through a particular material. Some materials are like superhighways for heat, others not so much.
So like some materials are better conductors than others.
Exactly. And we quantify that using something called the K value. For instance, copper. Copper's famous for its high thermal conductivity, way higher than, say, stainless steel. That's why you see copper cookware everywhere. It heats up super quickly and evenly.
Makes those picture-perfect pancakes. So if you're looking for a material that's great at holding onto heat, like for a nice slow simmer, you'd want something with a lower K value. Is that right?
Exactly. Something like cast iron, maybe.
It's amazing how this like simple table comparing thermal conductivity values can totally change the way you think about choosing cookware. Who knew?
It really highlights the practical side of understanding these principles. It's not just theoretical, it's stuff you can use every day.
Okay, so we've tackled conduction. What about convection? That's the one with the moving fluids, right? Like liquids and gases.
Right. Think about a pot of water on the stove. As the water at the bottom heats up, it becomes less dense and starts to rise. Meanwhile, the cooler water at the top, it's denser, so it sinks,
Creating a sort of flow.
creating a flow. We call these convection currents. And they're constantly moving and grooving, distributing heat throughout the fluid.
It's like a dance floor, but for molecules.
Exactly. And if you want to speed up the party,
Mm-hmm.
just add a stir. That's the difference between natural convection and forced convection.
Okay, so with natural convection, those currents, they're just doing their own thing. But when I stir, I'm like introducing those molecules to new dance partners.
That's a great way to put it. You're essentially creating forced convection, speeding up the heating process. And this principle isn't just limited to your stovetop either.
Oh, really?
It's how those massive ocean currents are formed, how weather patterns develop, how hot air balloons rise.
Wow.
It's everywhere.
It's amazing how these tiny little convection currents are actually driving huge things like ocean currents. It's
Oh, yeah.
wild.
It really is.
Yeah.
It just goes to show you how these fundamental principles of heat transfer are working all around us, often in ways we don't even realize.
Speaking of things we don't always see, let's talk about radiation. That's the third way heat can travel, right?
Yeah.
And it's how we feel the sun's warmth, even though, we're millions of miles away.
Right. Radiation is how heat travels as electromagnetic waves, kind of like light.
So it doesn't need a medium, like a solid or a fluid, to travel through.
Exactly. It can travel through the vacuum of space, which is why we feel the sun's energy, even though there's literally nothing between us and the sun.
It's kind of mind-blowing when you think about it, but radiation isn't all about sunbathing and, getting a tan.
Definitely not.
It has a lot of practical uses here on Earth, too.
Absolutely. It plays a crucial role in a lot of industrial processes.
Yeah.
Like our source actually mentions how it's used in pharmaceutical drying.
Oh, that's right. It's used to dry delicate pharmaceutical products without, damaging them.
Yeah.
Okay, so we've covered the three main ways heat gets around: conduction, convection, and radiation. Let's talk about how they all work together, because our source mentions this thing called a steam bath.
Okay.
And I have to admit, when I first read about it, all I could picture was a luxurious spa day.
Right.
But it turns out a steam bath in a laboratory setting is a whole different ballgame.
It is. It's not about relaxation, that's for sure. But it is a really cool example of how all three of those heat transfer methods we just talked about, they can work together.
Okay, so walk me through it. What's actually happening in a lab setting when we talk about a steam bath?
Okay, so picture this. You've got a simple setup in the lab. You've got a gas burner, right?
Okay.
And it's heating a container of water.
Okay, like a pot on the stove. Got it.
Exactly. So the heat from that flame, it's transferred to the container through direct contact, right?
Right. Conduction.
Conduction. And then that heat is transferred from the container to the water, also through conduction.
Makes sense.
And as that water absorbs more and more heat, it eventually reaches its boiling point.
Okay, so far so good. This is the part where, in my spa day fantasy, I'd be grabbing a fluffy robe.
Right. But in the lab, things get a little more scientific. This is where the magic of latent heat comes in.
Latent heat. Okay, you're losing me a little bit.
So latent heat is basically the hidden energy that's required to change the state of something, like water, without actually changing its temperature.
Wait, so the temperature doesn't go up while the water is, transforming into steam?
Exactly. It's
Yeah.
like all that energy is going into breaking the bonds between the water molecules so they can make that leap from liquid to gas to steam.
Wow. That's pretty cool. It's like hidden energy reserves.
Exactly. And here's the aha moment. That steam is now carrying all this extra energy, that latent heat, rises, and it hits a cooler surface, like, say, a dish with some delicate pharmaceutical substance in it.
Okay.
And as that steam condenses back into water on that cooler surface, guess what?
What?
It releases all that stored up latent heat, and that provides gentle, even heating to whatever's in that dish.
So it's not really a water bath. It's more like a steam bath.
Exactly. And that distinction, it's really crucial, especially in pharmaceuticals.
Mhm.
Direct contact with boiling water, that can be too harsh. You could end up ruining those sensitive pharmaceutical ingredients. But the steam,
Much gentler.
exactly. It's all about precision and control in the pharmaceutical world.
So it's like the difference between blasting something with a hairdryer on high heat and letting it air dry gently.
Perfect analogy.
Yeah.
And it all comes back to understanding the nuances of those three heat transfer methods working together.
That's so cool. Okay, so we've talked about how heat can sometimes be our enemy in the kitchen, like with my poor charred casserole. But sometimes we want to like trap that heat, keep it contained, and that's where insulation comes in, right?
Exactly. Insulation is all about controlling heat transfer, about minimizing that unwanted heat loss, or in some cases, heat gain.
And we do that by using materials that are good insulators, right? Materials that are kind of like those friends who are always warm and cozy, even on a chilly day.
I like that analogy.
So what makes a good insulator?
It all comes down to thermal conductivity again. Remember how we were talking about K values before?
Yeah, the lower the K value, the better the conductor.
Right. But with insulation, it's the opposite. You want a material with a really low thermal conductivity because that means it resists the flow of heat.
So it's like a heat bodyguard.
Exactly.
Our source mentions a bunch of different materials that are good insulators. Some of them are kind of surprising, like cork. I mean, we usually think of cork as something you find in wine bottles.
Right. But it makes sense when you think about it.
Yeah.
Cork has an incredibly low thermal conductivity, which is why it's so good at keeping that wine at just the right temperature.
It's like a tiny little jacket for your wine bottle. That's so cool.
It really is. And then you've got things like 85% magnesia. It sounds kind of mysterious, but it's actually used a lot in industrial settings to insulate pipes.
To prevent heat loss.
Exactly.
Yeah.
Especially in places like power plants and refineries where, they're working with really high temperatures.
Makes sense. And then, of course, there's the classic insulator,
Mm.
fiberglass insulation, which you find in like attics and walls.
Right. It's great at keeping those cold drafts out during the winter.
It's like giving your house a big warm hug. This deep dive into the world of heat transfer has really opened my eyes. I had no idea there was so much to know about how heat moves and behaves.
It's a whole invisible world, but it has a huge impact on our lives. It affects everything from the way we cook our food to like how we design buildings.
Speaking of design, I was really intrigued by this idea of economic thickness that our source mentions. It suggests that there's actually like a point where adding more insulation isn't worth the extra cost.
Right. It's a balancing act.
Yeah.
Adding more insulation will generally mean less heat loss, so
Yeah.
you'll save energy, which is good for the environment and your wallet. But at a certain point, the cost of adding even more insulation, it might not be offset by those savings.
So it's about finding that sweet spot where you're maximizing energy efficiency but also keeping an eye on the budget.
Exactly. It's kind of like adding layers of clothing on a cold day. At some point, adding one more sweater, it's not going to make a noticeable difference. And you might be better off just turning the thermostat up a degree or two, even if it means a slightly higher heating bill.
It's all about finding that balance between comfort and cost effectiveness. Who knew that understanding heat transfer could help you make smarter decisions about your home insulation? This is why I love these deep dives. We're learning so much. It really makes you realize that insulation isn't just about like comfort, it's also about, making smart choices, being energy efficient.
Absolutely. And it all comes back to understanding these fundamental principles of heat transfer.
Exactly. So next time you're enjoying a nice hot cup of tea, think about all the amazing heat transfer action happening right in your hands.
It's true. You've got conduction happening as the heat travels from like the hot liquid through the mug to your hand.
And convection currents are swirling that liquid around inside the mug.
And there's even a little bit of radiation happening, warming your hand from a distance. It's like a silent symphony of energy transfer.
And we get to experience it every single day. This deep dive into the world of heat transfer has been amazing. I've learned so much.
Me too. We've gone from like the very basic definition of heat all the way to these really practical applications like how to insulate our homes and why steam baths are so important in pharmaceuticals. And it all started with this university course document on industrial pharmacy.
It just goes to show that, even these specialized fields, they can offer insights that are relevant to everyone.
Absolutely. It's all about making those connections between scientific principles and how they play out in the real world.
So as you go about your day-to-day, I challenge you, try to notice the ways heat is being transferred all around you.
Like how the sunlight feels warm on your skin or how a cool breeze can be so refreshing on a hot day.
These invisible forces of heat transfer, they're constantly shaping our experiences.
And understanding them, even just a little bit, it gives us this whole new appreciation for the world around us.
Well said. It's been a fascinating journey into the world of heat transfer. Until next time, keep those minds curious.